Hello everyone, welcome to this tutorial. My name is Xiaoyong, and we have a few colleagues here like Mason and Ivan and Wilson joining me today. So we will be hosting a tutorial on how to build intelligent mobile applications in healthcare. So this will be the agenda for this tutorial. So basically we will spend a few minutes introducing the background a little bit, and we will have Mason, who is a resident radiologist from University of Washington, walk us through why it's an important thing and what's the clinical decision-making process in the real clinical settings. And my name is Xiaoyong, and I come from Microsoft. My focus is primarily on image processing and especially on medical images. So I will walk through how to build a actual model to recognize chest X-ray images and detect the diseases there. We will have two parts there. So the first part is that we will use a pre-trained model so that you can use the pre-trained model to see what's happening for the real-world chest X-ray images. And the second part is that if you really want to build the model from scratch, we also have a tutorial on how to build the model from scratch on chest X-ray images. And after that, we will have a break for like 10 minutes. And after that, we will have a tutorial on how, after you have the model, how you can build the model into a application that the doctors or like other people can actually use. And finally, because this is more for all the tutorials, this is still sort of like a prototype. And finally, we will have a very serious production-ready AI on medical images presentation by Ivan from Microsoft, from the InnerEye team. So hopefully everyone has a small piece of paper on your hand. If you don't, like this, with the number ranging from 10 to 40, I think you can grab some more in the desk. Yeah. So basically, we will have this tutorial running in the Jupyter Notebook. I will show this in the tutorial part, but basically it's like a tutorial server, and you can just log in it. All right, so without further ado, let's start with the first part with Mason on why this is an important problem and how actually clinicians think about this.
Hey guys, well, thank you for coming out. Basically, my name is Mazen Zawad. I'm a chief radiology resident at the University of Washington, and I believe the future of medicine is basically at the intersection of medicine and AI, and my goal is to help individuals working in both worlds kind of intelligently speak with one another using a systematic framework in a similar language. So with this talk, I'm just going to kind of give you a little bit of a bird's eye view of how a clinician thinks, but in a way that you can kind of use when building applications so that it best serves everyone involved. And the talk objectives are to establish a common language and thinking processes between clinicians and data scientists/engineers with regards to diagnostic applications, describe a systematic approach to clinical decision making, define best practices for reporting diagnostic performance metrics. So once you've trained your model, how do you report those performance metrics to physicians in a way that they can understand it? And help you all generate focus questions for clinical domain experts, healthcare workers, by using the above framework. Broad overview, what are the features of an ideal diagnostic healthcare app? Ultimately, diagnosis and clinical decision-making is about belief about the presence or absence of a disease, risk, how risky is this entity that I'm going to be treating, and the actions that the healthcare worker is going to take thereafter. And so an ideal diagnostic healthcare app is going to help the clinician either change their belief about the presence or absence of disease. If the clinician knows a disease is present, what class of disease is present? If it's fairly intuitive and we know that a particular disease state is present, quantify the severity. And in the end, if the diagnosis is really simple, then the application might make the whole process faster or simpler. And so where does this all fit in? The clinical encounter. So right now, we're going to basically everyone put their white coat on. You guys are the clinician in the emergency room. And these are our stakeholders. We're all the consulting physician right now. We're an emergency room physician. We have our patient that we need to take care of, and there's a radiologist that's going to help us out. And this is where we're going to start developing that clinical framework. Patient Susie comes in, she has cough and fever. And you as the consulting clinician now is thinking, I wonder if Susie has pneumonia based off of what she's showing me here. And the framework that we can all use is what I call semi-quantitative Bayesian thinking. And this is kind of a reorganization of the Bayes theorem that you're all comfortable with, presumably, but instead framed in terms of odds rather than probabilities. Because in medicine, a lot of the time when we're looking at a diagnostic test, we think of something called the likelihood ratio, which is a quick and dirty number that tells us how we should change our belief about the presence or absence of a disease, both in quantity and in direction. And so we as emergency room physicians right now, pretend emergency room physicians, need to figure out the prior odds that Susie has pneumonia. And this is just the equation set up as probabilities. So this is us right now. And the prior odds in medicine are based off of a clinician's prior experience, the history that a patient gives you, the laboratory values, and the physical exam. This is something that you guys will not have to deal with when you're building an application, but you want to have an idea of how the clinician thinks beforehand so that you know how to best tune the application to basically change their posterior belief. And there, in medicine, this was published in the British Medical Journal, basically. We try to bin, because this is very subjective, we try to bin our prior beliefs about a disease state into these rough categories. Things that are very unlikely or very likely may not need a follow-up test, and this might not be the hotspot for applications to be developed because the clinician is really quite certain the disease is either absent or present, and numerically this is, let's say, less likely than 10% or more likely than 90%. Applications could be useful in this domain, just as an aside, if the disease is very unlikely to be present, but is extremely high risk, and the diagnostic test is low risk. So let's say you develop an application that has a very good predictive value and can sway the clinician to say, okay, there truly is no disease present here, even though I know this is extremely risky if I miss it. And the counterpoint is, if I know a disease is present, or I'm almost near certain, but I want to make sure that it's almost 100%, because if I treat this patient, it could be very noxious if the treatment goes unwell. An application could help you bump up to that level of next level of certainty. The sweet spot for you guys, though, is where the clinician says, you know, I'm not really sure. It's this kind of indeterminate range. And that's where further testing can help change a clinician's belief. So for an effective diagnostic test, this is kind of a useful rule. A positive test result should move you to the next more likely category, and negative results should move you to the next less likely category. And I'm going to show you later how you're going to quantify that when you're building an application, basically. So let's say we say, okay, pneumonia is likely. In our prior chart, we know that's about 80%. Let's get a chest x-ray. We want to change our belief a little bit here. So we say our odds are 4-1, changing the probability of 80% to odds. And now take off the white coat. We're entering the world of applications, or in today's world, the radiologist who's going to be dealing with the medical imaging data. And so we get a chest x-ray, and this likelihood ratio, every diagnostic test has an associated likelihood ratio. And the likelihood ratio says, what direction am I going to change my belief about the presence of disease, and how much? And so in the radiologist world, the way we do this is we have a list of patients and a list of imaging studies that we need to read. So this is Susie's chest radiograph. I'm going to say, okay, is pneumonia present? And it sure looks like it. It's this white stuff here in the corner. And I'm going to, in today's world, what we do is interpret it, have a report that's set out, and that report communicates these findings to the clinician. The clinician then says, okay, the chest x-ray is positive. I know reported in the literature, this is the likelihood ratio for this exam. These are the posterior odds. We're very likely that pneumonia is present. We're going to treat the patient. So where does AI fit in on all of this? And basically, one can create applications for either disease classification, localization, semantic segmentation, all of these different use cases. But in the end, what you want to be able to report to the clinician is, how is this going to change? how is this going to change your belief about the presence or absence of disease? And so the metrics you want to report are sensitivity, specificity, which therefore the likelihood ratio can be calculated, and also the area under the curve, and we'll go into that in turn. In terms of actual use cases, exams that are very, very sensitive, which are like meaning they can pick up disease very easily, but sometimes overcall the disease, they would be useful basically in helping people triage whether disease is present. So if I know my app is going to say disease is present every time it's present, I can look at my work list and say, okay, my application says the disease is absent, and so I can leave those behind. The counterpoint to that is if an application is very specific, meaning every time it says a disease is present, it's almost there with certainty, I can triage that and say, okay, I need to tend to these exams first. And this is just a reminder that not every use case is a diagnostic application. And there's a whole radiologic value chain in where AI could really be injected into any of these steps. Today I'm focusing on diagnosis, but there's a whole world out there where these applications can help make things either faster or better. And this is just one example of where this is not a diagnostic application, but one in which you're doing super resolution imaging from initially a noisy MRI and using a trained model that knows how to correct for that noise. So let's say you build a prototype application, which we'll be doing in just a minute. You need to know when your system is good enough to deploy in a clinical setting. And to do that, you're going to need to have a gold standard or a reference test comparison. And that's going to fall into the realm of diagnostic accuracy, which again, I mentioned sensitivity, specificity, predictive values, and ROC curves. I'm going to go into that in a moment. And you want to compare those values that you calculate from your model compared to the gold reference standard. A lot of the time, the reference standard in medicine is going to be histopathological diagnosis, meaning you take tissue out of the patient, look under it grossly or under a microscope, and that's going to be what you want to compare your application's performance to. And if that's not available, then it's going to be a congregation of experts. Let's say 5 expert radiologists look at an image. They perform at a particular sensitivity, specificity, and at a certain point on the ROC curve. And you want to make sure that your application, you're able to report those metrics as compared to the gold standard. And this, I don't want to go over it in detail, but if anyone wants to talk about this offline, basically this is the way that the likelihood ratio is calculated on the basis of sensitivity and specificity and their complements. And that's what a clinician is looking to hear if you're trying to pitch a certain product. How is this going to perform in my patient population? And you want metrics that are invariant to different populations, and these are such metrics. And this is the ROC curve, and in today's tutorial, we're going to be measuring the area under the ROC curve, and we can go over that in the tutorial. So this is the last slide here, App Builder's checklist. So talk to your clinicians, identify relevant use cases, don't operate in a silo. Research the clinical problem using efficient, comprehensive resources such as UpToDate, which is a website where it's relatively easy to get a really good idea about disease states in an easy, single, comprehensive location rather than going and rifling through the literature. Identify the current diagnostic gold standard and obtain those performance metrics and use those as your reference point for when you're building your application. Make sure you curate a data set with ground truth labels that are assigned using the gold standard so you don't have kind of fuzzy labels, you have really strong labels. And then develop the application with the mindset of either matching or outperforming the gold standard while making the process potentially simpler, faster, or more cost-effective. If you have any questions, please ask me now, or you can email me at this email. Thank you very much. Any questions? Yes. Yeah, I'll have to submit them, but they should be available. Okay, and I will. I'll follow. Yeah, I'll follow up with you as to where I have to sort that out. Any other questions? All right. Yes. Well, today we're going to be focusing on pneumonia detection, but there are many other projects. For example, detection of intracranial hemorrhage on non-contrast CT scans used as a triage tool. Ivan later is going to be talking about segmentation tests and more accurate quantification of disease states, and I'll let him kind of elaborate on that. But there are numerous use cases, and been working on several. But today we're going to be focusing on detection of pneumonia from chest X-rays as well as other disease states on chest X-rays. Anyone else? Okay, thank you. Oh yes, go ahead.
So the images, where did you get those images from? Public data set or?
Oh yes, we're going to go over that in just a moment. But the chest X-ray data set, the NIH released, and it's a public data set. That's all right. Thank you.
All right, let's go to the tutorial part.
Not showing it.
It's not showing. Let me see. Okay, cool. So, hopefully everyone get a number on a small piece of paper.
Is there anyone who does not have
So this is the tutorial server. So if you go to this IP address in your browser, you should log in using that particular user. So basically the address is like this. Let me see, it's not presenting. My PowerPoint died, sorry for that. So if you go to this, duplicate the screen. Yes, okay. So if you go to this address, so first remember to use HTTPS, otherwise it won't go through. And the username would be X-ray user with the number you have. The number should be ranging from like 5 to 40. And the password is X-ray user PW. So you will probably receive a warning like this saying this site is not secure, but trust me, it is secure. So you may want to click like details, and there should be something said like go to the web page, not recommended, and yeah, you should click that link. That will bring you to the actual test server. So for those of you who have already logged in, there's a very deep folder structure. So you need to go to Azure Chest X-ray and go to Azure Chest X-ray AML WB, go to code 04 tutorial, and let's open the first tutorial for now. Okay, so yeah, by the way, for those of you who don't have access to the notebooks, you can also go to this Jupyter GitHub repo called, you can just search for Azure Chest X-ray. It's this link. It's github.com/Azure/Azure Chest X-ray. So basically it have the same folder. So you can just click through the folder structure and you can visit all the Jupyter notebooks there. Okay, so let me make it full screen. So basically in this tutorial, we'll walk you through how you can build a lung disease prediction model using chest X-ray images on Azure. So first, this machine is on Azure. So that's the very basic Azure part, but we'll also see a lot more Azure parts coming later. And so also Mason introduced a little bit on why this is like an important problem. So pneumonia and actually other lung disease, they are super lethal, and actually 18% of the child deaths worldwide are caused by pneumonia, just this one particular disease. And actually, nearly all of them, they are in developing countries. Like I come from China, and in most of the parts in China, pneumonia isn't that lethal, but in some of the undeveloped area in China, like pneumonia is also very critical disease. So this disease is killing people, and another part is that we don't have a lot of access to radiologists. So the World Health Organization estimates that actually 2/3 of the people in this planet don't have access to basic radiology services. So actually, for example, in Africa, most of the country just have like a few dozens of number of radiologists, while here in the United States, just for a single hospital, we have like 200 or like about 100 radiologists. So that makes us think, how can AI help in this particular case? So there are a few use cases there. So as Mason just showed, so for radiologists, basically they need to look through every patient and every chest X-ray in a column fashion. If you take closer look at this picture, where on the left they have like this huge screen where listing all the like the patients and the income like chest X-ray. So in that case, probably one of the things we can do is that we can just sort those incoming images by like likelihood. For example, this particular chest X-ray image or this particular patient have high probability of a disease, or in some other cases it doesn't have disease at all. So we can possibly do that. And another thing we can do is that we can also help radiologists to diagnose if they trust the AI algorithm. So in this Jupyter notebook, basically we will build a classification model for chest X-ray images, where finally we will be building a model that can classify chest X-ray images that have like a human radiologist level of accuracy. So let me introduce the dataset a little bit more. So this is, as one of the audience just asked, so this is actually some public dataset. That's actually one of the biggest public dataset for chest X-ray images. So the reason there is that for most of the chest X-ray images, for example, if you go to the hospital, you say, okay, I want to do some AI on chest X-rays, just give me your data. They won't trust you, of course. So in that case, so that's one part. Another part is that even they trust you, they say, okay, go with the data, and you actually don't have labels, because it needs like very professional people like Mason who need to like label the data and say, okay, this one has pneumonia, the other one has some other diseases, etc., etc. So actually, you need to pay them to label the data. So what NIH, this team does is that they are actually very smart. Instead of asking radiologists to label the data, they say, okay, why don't we label the data using the patient history? Because there are a lot of like information in the patient history saying this patient probably they are smoking, so they have a high likelihood of getting this kind of chest diseases, etc., etc. So in that case, they actually use an NLP algorithm to mine the patient history and then use that history as the label. So people may ask, okay, this is not like 100% accurate labels. So people may question about the performance of the label itself. But actually, it turns out the label is pretty robust in terms of the final accuracy. So we will go through that a little bit more. And partly of the reason is because the data set is actually very huge. So it has like more than 30,000 patients in the data set, and we have like over 100,000 images in the data set. And we have like 14 different pathology labels like atelectasis and pneumonia, etc., etc. So as we will see, actually those it will be very hard for human radiologists to actually label them. But with this kind of NLP algorithm, it's actually quite easy to get the labels. So first, the first part of the tutorial, in the first part, we will go through the using how to use the pre-built model and see, test the first success there. So I'll run this cell. Basically, it will import like TensorFlow and Keras, etc., etc. So we will be using Keras with the TensorFlow backend in this particular tutorial. And in the second cell, basically, it's like a few other settings. It will, so we already pre-downloaded the data and the labels in a shared folder. So the shared folder should be here, where it's under user local share and X-ray tutorial. So if you, so with that particular user and password, you can also access this server through SSH if you really want to take a look at all the data there. So first, one of the most important thing that we want to visualize the data a little bit before we actually do anything for the dataset. So let's take a look at the data. So here we will read the data. So we have we downloaded 1% of the original dataset. So it should start with some number like this, where the 700 here stands for the ID for the particular patient, and the 000 stands for the index for the images for that particular patient. So in this case, this is the first image for the patient ID, which is 700. So we can visualize this, or we can visualize some other data of this patient. So if we change the label to 001, then we will have a different image here. And for this particular case, we will use a network architecture called DenseNet. So I'm not sure how many of you have heard about this particular network architecture. DenseNet? Okay. And how many of you have trained at least one like image classifier before? Okay, cool. So let me go through some basics there. So the basics there is that first we want to frame this problem as a image classification problem. So what is a image classification? So the problem is that, for example, on the left of the picture, we will see that there are a lot of puppies there. And for the computer, actually, it doesn't see all the nice thing that we can see. Actually, it sees a bunch of numbers like on the right, where it's like for the green grass, it's like 0.8, and for the white skin, it's like probably 0.0 or something like that. So basically, it sees a bunch of numbers. So that's actually a image that is actually stored on the PC, on your hard drive. So in that case, we actually have a few different computer vision tasks. So we have this task called image classification, where we have this input image, and we will classify whether there's a deer in the image. If yes, we say yes. If no, we say no. Whether people have pneumonia in their chest X-ray images. If yes, we say yes. If no, we say no. Something like that. That's called image classification. And we also have a few other tasks. For example, people will have object detection task, where people really want to locate where's the interest object there. For example, if after we have this deer on the picture, people may ask, where is the deer, right? And in the case of pneumonia, people may ask, like, why do you classify this picture as pneumonia rather than like atelectasis, etc., etc.? So people will ask this question. This is called object detection. And the third part is that image segmentation, because for the object detection, we will have this kind of yellow bounding box for the object of interest. But for the image classification, people want to know exactly pixel by pixel of why this is like where's the object is. So we will also introduce, we will also have a quick discussion on this in the InnerEye project. So those are a few of the image classification tasks. And before deep learning, there are a lot of different approaches to deal with those kind of image classification tasks. So basically, the idea is that because we have something in the picture, probably we can extract some of the features in the picture. For example, there's a bike, and the bike itself, the foreground object must be very different from the background object, something like that. So in that case, people have a few smart ways of dealing with those kind of situations. So for this particular case, we have a bike here in the picture, and we do some image processing. And after that, we will have this kind of, it looks like a bike, but we extract a lot of features there, and we will have this picture passing through a final classifier, and we will have a classification model saying, okay, whether there's a bike or whether there's something else. So that's before deep learning. And for this, and as you can imagine, this is actually very dependent on the image itself. For example, if today we have a bike image, so we can extract those kind of features. But tomorrow we are developing this chest X-ray images. So in that case, probably those kind of features or those kind of algorithms won't help at all. That's how deep learning can help here, because deep learning is like a method where it does those kind of feature extraction automatically for you. In that case, we'll have a huge neural network. We call them, most part of the neural network is called convolutional layers, where people will have an algorithm that is looking at different parts of the object or of the input image, and we will say, okay, whether this particular image have some interesting things that we can learn or the algorithm can learn. So in this particular case, for example, if the input is a cat, then we will have this sort of convolutional neural networks, and different layers will actually act as different, we call them different featureizers, but you can just think them as different learning brains. For example, one of the layer will learn something about the color, another layer will learn something about the lines, etc., on this particular image. So basically, we will have a huge neural network, and that will we don't need to care about anything about feature extraction, and this particular neural network will read through an image and give us some output saying it's a cat, it's a dog, or in medical image case, it's, let's say, it has a particular disease. So that's how deep neural networks is utilized in computer vision. And another particular case is that if you have trained some classifier before, some deep neural networks before, you may know that actually we need a lot of data to actually train at least one algorithm. For example, we want to train a medical image classifier. So in that case, in most of the cases, actually, like we need a lot of data. For example, in this NIH dataset, we have like more than 100K dataset. But what if you want to train on your hospital's particular dataset? You probably don't have that much of data, and probably you don't have that much labels. So in that case, what we do is we usually do transfer learning there, where we use the knowledge of the sort of the ancestors of the neural network. Because the neural network, we can first train the neural network on some particular public dataset. For example, in this case, we will train the neural network in this chest X-ray image public dataset. And then if you want to apply it in your hospital, you just need to fine-tune it with much less labels, with much less data on your hospital's image dataset. In that case, it will save a lot of labels, save a lot of human effort there. That's the basics for image classification and transfer learning. So any particular questions there? Okay, so let's go back to our first tutorial. So, so basically, we frame this as an image classification task. And the first thing we need to do is that we need to select the right model to do the image classification, to do the final image classification task. One thing that we are very interested in is that because there are so many different neural network architectures available here, so we can say we use, there's one particular architecture called Inception, which is widely used in this kind of image classification background, in this image classification world. And we also have like different models here. But for this particular model, for this particular project, we use a model called DenseNet. Basically, the key idea there is that instead of, so the key idea there is that in deep neural networks, it's actually very hard to pass the information through each layers. For example, we will have the final prediction layer which has, in this particular case, it's it's a horse classifier where it's classifying whether it's a horse or not. So if the final classification is wrong, then it must pass the final prediction into the previous layers, telling each of the layers, saying, okay, you have made some mistake, you need to correct them, etc., etc. So the information passing part is super important for all the deep neural networks. So that's why when people talk about deep neural networks, sometimes they say like 10 layers, that's already considered as deep, or sometimes they say like 100 layers, that's also very deep. So in order to achieve the architecture innovation from like 10 layers into 100 layers, the smart thing people need to do is that they need to figure out an innovative way to pass through the information from the 100th layer into the first layer. So that's the hard part, and that's how DenseNet comes in. The key point of this DenseNet innovation is that it helps to pass the information from the, like, let's say the 100th layer into the first layer. So the innovation, the key idea there is that instead of passing the information layer by layer, let's say we have all the layers densely connected as shown in this image. So in that case, we don't need to pass. So in this case, we don't need to pass the data, pass the information through the layer. For example, this layer to this layer to this layer. Instead, we will have a densely connected block where in this block every layer is connected. So in that case, every layer can talk with the other layer. Even let's say we have like a 100 deep, like 100 layer deep neural network. The 100 layer can still talk with the first layer. So in that case, it can just make sure that the information flows correctly for each of the layer. So in that case, it helps to alleviate the problem of gradient descent. That's the key idea of DenseNet. And in this particular case, actually, because we are using Keras, so Keras actually has a pre-built neural net architecture for DenseNet. So what we do is that we will just use this. So because we already imported it from Keras, so if we run this cell, then it will build this DenseNet architecture for me. So for this particular case, we will have, because we also want to use transfer learning here, otherwise it will cost us too much trouble. So what we do is that we will initialize the model using the ImageNet pre-trained weights. Basically, the key idea is that the model is already pre-trained on some other datasets, but the dataset is focused very much on like flowers or birds, etc., those kind of common objects in our lives. And but we want to take over that knowledge that the neural network has already learned and apply that to the chest X-ray images to use less data and to convert the model more quickly. So in that case, what we do here is that we have this DenseNet image, DenseNet model, and we won't include the final classification layers because we are not classifying for ImageNet dataset. We are classifying for this chest X-ray dataset. So what we do is that we will add another classifier based on the DenseNet architecture. So our final output will be 14 diseases, which is the final label for the NIH dataset. So for this function, basically, we build the model. And this is the loss function. Basically, you can use, in this case, we use the binary cross entropy. Basically, it's like, so if you are familiar with the sigmoid classifier, basically, this is like a sum of all the sigmoid output. So this is basically the model. So from the model, we will see that we built a classifier that can classify like 14 diseases. We will go through the training part a little bit more later. But let's say we have already gone through the training part and we already have a model. So the next step is that how do we actually apply the model there? So in that case, you want to run through this cell to to see how the model performs on the final data set. So usually a image classification model will just give you a output saying, okay, I detect something. For example, I detect pneumonia, which is like 80% confidence, something like that. But probably that's okay for like regular images like buildings and cars and birds, etc., etc. But for this particular problem, for the medical images, if you go to a hospital, some AI algorithm will say, okay, man, you have pneumonia, go to some other doctor to treat it. And you ask the AI, okay, why do you say that, right? And you won't, in most of the cases, you probably won't trust it. So in that case, like how to interpret the model, how to visualize the model, that's super, super important for the medical images. So in that case, we are not only going to predict the single value of the disease, but we are also going to visualize the model so that people can know what's going wrong and why the AI model is predicting something. So we frame this as a model visualization problem. Basically, this is one of the results where on the top left, we will have the original input image, and on the right, we will have the predicted sort of interesting area. So, and on the bottom left, we will have those two images sitting on top of each other. So we'll have this overlapped image. Basically, you will see that, okay, the AI model is thinking that something is wrong for this particular X-ray image here. And on the last image, the red bounding box is the one that is labeled by the radiologist. So actually, you can see that it's pretty close. And this is like a visualization of cardiomegaly where the patient actually have a, let's say, a big heart here. So you can see that the white area here is actually stands for the heart area of the patient, and the AI model actually predicts that area actually very accurately. So let's go through the science behind it a little bit more. So the technique we are going to use here is called class activation mapping. So the key idea there is that because as I just said, each layer in this particular neural network, they will see different features of the image. For example, the input here is like probably a man with a dog, a kid with a dog. And each layer will focus on different parts. For example, the first layer will focus on the face, and the second layer will focus on the leg and the head of the dog, etc., etc. So each layer will have a different focus there. And the key idea of this class activation mapping method is that it will have a smarter way of weighting different layers, and it will aggregate all the visualizations together. And finally, for example, in the first layer, probably it will give it a little bit weight, and for the final layers, it will probably give a lot more weight. In that case, it can visualize the whole model. And in this case, we will have this, because we are trying to build a dog classifier here. So in this case, the model is really focusing on the dog itself. So basically, when it sees something like a dog, it will focus on the dog, and it will predict something saying, okay, this is the dog. And go back to our chest X-ray images. We want to show that, okay, for example, if the model is detecting something as pneumonia, then we really want to show the area that is considered as pneumonia, and we really want to make sure that the model can predict things correctly. So first we're going to run this cell. So in this case, we are going to load the model. So I already downloaded the model into the shared folder. So when you run this cell, basically it will run through the loading part, and it will load the model here. And then we will summarize the model. The model will be like this, where it's hard to show here, but basically it's like 120 layers, I believe. And it will have something like this is the input layer, and you have a lot of different layers in between, and you will have the final layer, which we call it a dense layer, and the dense layer will have a 14-dimensional output indicating. So each of the dimension there will indicate one of the particular disease. So we have loaded the model here, and I think I need to run through some other code. So let me run through this. And for this particular cell, we will visualize some image. In this particular case, we are visualizing the image. The patient ID is 728, and we are visualizing the first image there. And we will print this image out, which is like this. And you can also try to visualize some other images. And the next part is that how do we actually get the score for the model output, and how to visualize the model through the class activation map thing we just mentioned. So the key part is that we have this function called getScore and CamPicture. So the key idea is that we will get the final classification score for the model plus the final visualization matrix. So this is like some super long function. I won't go through that, but that's basically the key idea there. So let me run through this cell a little bit. And then this is this cell is the final display kind of cell. So basically, it will run through the model, and for the particular input image, it will show whether there's something wrong with the particular image. So again, we are using Cardiomegaly for reference because it's actually very easy for us as regular, person to take a look. And for this case, we are visualizing this. Image. The original image is here, and the model thinks something is wrong in this particular region, and we overlap the activation map on top of the original image, and we will get this result where the model thinks something is wrong here. And of course, we can try out different images here by changing the line here. Okay, so this is the first part for this tutorial, and I'll have like 10 minutes here in case you just want to run through the whole notebook, and in case you want to try different images there. Have people run into any troubles? No. Sorry, there was a question. Yeah, like you can just modify this line. So this number should be ranging from 700 to 800 because that's the dataset that we download for this tutorial. And this index number, you can keep it as 000, but sometimes you can also change it to 1 or 2. Sorry, what's the question? Oh, yeah. Yeah. Uh-huh. Yeah, so the yeah. Uh-huh. Yeah, that's actually a great question. So we will cover that later, but yeah, we'll cover that later. For this particular model. So I can show that a little bit. So I think it's in the second part of the tutorial. So it's let me show this. So so here we are showing this the thing we call in data science is called like ROC curve. So basically the key idea is that you can change the threshold, and every time you change the threshold, it's like a point here in this ROC curve. So the vertical axis stands for the sensitivity, and the horizontal line stands for the specificity, or 1 minus specificity. So the key idea. So this is the this model for this particular disease, which is pneumonia. So if you are predicting for like different disease, it will have a different ROC curve, like this. Does that answer your question? Uh-huh. So I think there are 2 points there. So first, you need to really train a good model. So if your model is really poor, then the ROC curve will be very ugly. So in that case, you definitely want to train a very good model where you have the you have the curve which is very close to this axis and this axis. So which will be like this. And the measurement we will usually do there is that we will have something called AUROC, which stands for the area under ROC curve. Basically stands for this area, like this area. So the larger this value is, then it means that we have a better model. So that's the first part. And the second part is that even you have the model which has a great prediction, then you still need to follow Mason's suggestion on what's the golden standard, or what's the final threshold, whether you should use like 0.4 or you should use 0.8 or something like that. So those are kind of 2 independent problems. So this tutorial focuses very much on the first part, where you need to build a great model. And then after you have a great model, you need to like choose the threshold very carefully, or the golden standard very carefully. So this is on the test data set. Yeah. Yes, exactly. So in order to do that, exactly. So in this case, people probably don't want to look at the graph, because that's not very intuitive to look at like 14 diseases or 14 graphs. So in that case, you may want to report the final score, like here, where you say, okay, I have an AOC score, or AOR. So AOC is like area under curve. So the larger this score is, it means that you have a much better model. So for example, for this particular model, it has like great prediction on, let's say, nodule, and probably some other disease, but or infiltration, but it's really doing poor on, let's say, consolidation or some other diseases. So they are really different for different diseases.